Optimization allows us to adjust, maximize, or minimize key outputs such as stress, mass, frequency, or any other parameter of interest. Hello, I'm Armin. In this video, we'll walk through how to use COMSOL's optimization tools to minimize the mass of a metal piece by increasing the radius of a hole, while keeping the stress within a safe limit using constraints. Before we begin, I'd like to give a brief explanation of the model. In the context of engineering, mathematics, and simulation, optimization is the process of systematically adjusting input parameters to achieve the best possible outcome according to a specific goal, while satisfying certain limitations. In more scientific terms, optimization is the process of maximizing or minimizing a particular quantity, called the objective function, by changing certain parameters called control variables within defined constraints. For example, optimization is commonly used in structural applications to reduce mass or stress. In cooling systems, it's often used to maximize heat transfer in order to minimize temperature. In this video, we'll focus only on structural optimization. In any optimization, we must define an objective function, the quantity to be minimized or maximized. It represents the goal of the optimization process. Common examples include minimizing mass, maximizing heat transfer in a heat exchanger, or maximizing natural frequency. Control variables are input parameters that can be adjusted during the optimization process to achieve the desired outcome defined by the objective function. These variables can include geometric parameters such as radius and thickness, or operating conditions such as speed, temperature, or applied stress. Constraints are limits or conditions that the solution must satisfy. They ensure that the design is feasible, safe, and practical. For example, you might limit the stress in a structure or set a maximum temperature for a device. The model is a metal piece subjected to a 1,500 Newton force. Since the geometry is symmetric, we can model only half of it. The bottom edge is fixed in the y direction, and the center point is fixed in the x direction to fully constrain the model. The geometry consists of a rectangle and a circle. The circle is subtracted from the rectangle using the difference operation. The solid mechanics physics interface is used. Boundary conditions include prescribed displacement, symmetry, and boundary load. A stationary study with optimization is used. The objective function is mass, which we want to minimize. As the hole radius increases, the mass decreases. Therefore, the radius of the circle is used as the control variable. The maximum allowable stress is limited to 25 megapascals, so this value is defined as a constraint. The figure on the right shows the initial model solution, and the figure on the left shows the model after optimization. The Nelder-Mead method is used for optimization. After the process, the hole radius increases from 1.5 centimeters to 3.5 centimeters, and a maximum stress reaches exactly 25 megapascals. The explanation is now complete. Let's start the modeling. First, I'm going to click on Model Wizard. The sample used in this tutorial is thin, so I want to model it in 2 dimensions. I'll click on the 2D button. Since I want to analyze the stress in the sample, I'll choose solid mechanics from the structural mechanics interface. Click on the Study button to proceed. As I mentioned earlier, I want to analyze the stress on the metal sample, so I need a stationary solver. I'll select it and click the Done button. Before creating the geometry, I want to define some parameters for the geometry dimensions. I'll go to Parameters 1 and set up a few values. I'll define R0 as 1.5 centimeters for the radius of the hole because I want to use this parameter in the optimization. It's good practice to include the unit. The thickness of the sample is 3 millimeters, so I'll define TH as 3 millimeters. Since I'm using these parameters for optimization, defining them is mandatory. Only optimization parameters must be defined. Before starting the geometry, I'll change the unit from meters to centimeters. Now I can enter the geometry dimensions in centimeters. Let's start by adding a rectangle. I'll right-click on Geometry 1 and select Rectangle. You can also add a rectangle from a Geometry tab or in the Sketch tab. I'll set the width to 8 centimeters and the height to 30 centimeters. Then click Build All Objects. Note that this rectangle represents only half of the model, and we will apply a symmetry boundary condition. Next, I'll add a semicircle at the middle of the part. I'll right-click on Geometry and select Circle. Since this is a half model, I'll change the sector angle to 180 degrees. Type R0 for the radius and click Build All. I'll also adjust its position by setting the y-coordinate to 15. Then, I'll rotate it 90 degrees clockwise. Everything looks good. Now I'll subtract the semicircle from the rectangle. I'll right-click on Geometry and select Difference. I'll choose the rectangle as the main object, enable Object to subtract, and select the semicircle. Then, click on the Build All Objects button. As you can see, the semicircle has been subtracted from the rectangle. The geometry is now complete. Next, I'll add a material to the model. I'll right-click on Materials in the Model Builder and choose Add Material from Library. From the built-in section, I'll select a suitable material, for example, structural steel. Once the material is selected, click Add to Component to apply it, and then close the material window. Now we need to specify the boundary conditions and set the thickness of the sample. Navigate to the Solid Mechanics Physics interface and click on it. In the Settings window, change the setting from plane strain to plane stress, since the geometry is thin and there is no stress in the out-of-plane direction. I'll enter TH, which was defined earlier as 3 millimeters. Everything looks good so far. Now we can apply the boundary conditions. Since the geometry is symmetrical about the y-axis, we should use a symmetry boundary condition. I'll go to the Solid Mechanics node, right-click, and select Symmetry from the More Constraints menu. Then, I'll select the 2 vertical edges along the axis of symmetry. To avoid artificial stress caused by over-constraining the model, we need to apply appropriate boundary conditions. Instead of using a fixed constraint, I'll apply a prescribed displacement on the bottom edge of the sample. Navigate to the Physics section, expand Boundaries, and select Prescribed Displacement. Choose the bottom line and constrain only the y direction. Since the geometry is under-constrained, we also need to prevent rigid body motion in the x direction. To do this, I'll fix the center point. Expand points under the Physics node. Select Prescribed Displacement. Choose the center point and constrain only the x direction. Next, I'll apply a force on the top edge of the sample to simulate stretching. I'll right-click on Solid Mechanics and select Boundary Load. Then, I'll select the top edge, change the load type from force per unit area to total force, and enter 1,500 newtons in the y direction. The boundary conditions are now fully defined. Now we need to generate a suitable mesh. Click on Mesh 1 and select Build All to view the default mesh. The mesh looks a bit coarse, so I'll change the mesh size to extra fine and click Build All again. The mesh now looks much better. Let's solve the model and check the results. Click on Study 1 in the Model Builder and hit Compute. The solution completes successfully. There is no artificial stress in the support region, so there shouldn't be any issues for the optimization. Before proceeding with optimization, I'd like to make a few plot adjustments. First, I'll enable the display of maximum and minimum values to highlight peak stress. It's also better to change the color map. Expand stress, go to Surface 1, and under Coloring and Style, click on the Color Table button. I think rainbow is a good choice, so I will select it and click OK. Now let's check the mesh independence of the solution. To improve the accuracy around the stress concentration, I want to add a boundary layer mesh. Right-click on Mesh 1 and choose Edit Physics-Induced Sequence, which allows us to manually adjust the mesh. I want to add a boundary layer mesh on the circular edge. Right-click on Mesh 1 again and select Boundary Layer. This option is also available in the Mesh tab. Click on the Boundary Layer properties, then select the semicircular edge. I'll reduce the number of layers from 8 to 6, which should be sufficient. After that, I'll click Build All to update the mesh. The mesh looks too dense, so I'll increase the stretching factor to 1.5 and build the mesh again. Everything looks good now. Let's rerun the simulation by clicking Compute. As you can see, the maximum stress has slightly increased, but the change is not significant. This means the solution is mesh independent and we can trust the result. Now, let's change the stress unit to megapascals. Go back to Surface 1, set the unit to megapascals, and click Plot. The maximum stress is approximately 19.9 megapascals. The simulation without optimization is now complete. In the next step, we'll prepare the model for optimization. To keep things organized, I like to rename Study 1 to Initial so it's easier to identify. Now I want to add a new study for the optimization process. I'll go to the Study tab and click Add Study. Since we need a static analysis again, I'll select another stationary study, just like before. Next, I'll right-click on the new study, go to Optimization in the menu, and select Optimization. Let me briefly explain the purpose of each section within the optimization interface. The optimization setup consists of three main parts: objective function, control variables and parameters, and constraints. The objective function is the quantity we want to either minimize or maximize. It can be mass, frequency, strain, or any results which we want to minimize or maximize it. In our case, the objective is to minimize the mass. Control variables and parameters are the design inputs that influence the objective function. In our case, we'll vary the hole size to reduce the overall mass of the structure. We'll add our 0 as a control parameter to adjust the size of the central hole. Constraints are used to limit specific outputs or behaviors of the model. In this example, we want to restrict the maximum stress to ensure it stays below a safe threshold. As the hole radius increases, the stress may also increase, so this constraint is essential to prevent the radius from becoming too large. Let's begin by adding the objective function. We need to calculate the mass of the sample after each iteration in order to minimize it. To do this, I'll navigate to Definitions, right-click, and select Mass Properties from the Physics Utilities section. By adding this feature, the mass will be calculated automatically during the optimization process. Now let's return to the optimization interface. Click Add Expression and select the mass expression defined under Mass Properties. This sets the solver to minimize the mass of the geometry. I'll keep the default optimization settings for now. Next, let's add the control variable. As mentioned earlier, the radius of the circular hole will vary during the optimization. Click the Add button to create a new control parameter. The radius is selected by default, and I'll leave it unchanged. Next, we need to define the lower and upper bounds for this parameter, which represent the minimum and maximum radius values during the optimization. I'll enter 1 centimeter as the lower bound. The upper bound, which is the maximum allowed radius, will be 6 centimeters. I'll leave the default scale unchanged. Since the radius is a single-digit value, a scale of 1 is appropriate. Finally, we need to add a constraint. We want to limit the maximum von Mises stress to 25 MPa to ensure structural safety. I need to add a probe to monitor the stress. To do this, I'll navigate to Definitions, right-click, and under Probes, choose Domain Probe. I'll set the type to maximum so it captures the peak stress value in the domain. By default, the probe is set to monitor displacement. We'll change this to stress by clicking Replace Expression and typing von Mises. The probe is now properly configured. Next, I'll click Update Result to see the current maximum stress in the geometry. I'll change the unit to MPa and update the result again. As you can see, the computed maximum von Mises stress is 19.64 megapascals. Let's compare it with the stress plot. The results are nearly identical. Now, let's return to the optimization interface. Click Add Expression, and from the Definition section, select the domain probe. Now, we can constrain the maximum stress to 25 MPa. In the upper bound field, type 25 MPa to limit the maximum von Mises stress to 25 megapascals. There's no need to specify a lower bound. With this setup, the maximum stress will be constrained and maintained at this threshold during the optimization process. Everything looks good so far. Next, I'd like to visualize how the geometry changes during the simulation. To do this, we need a plot that tracks stress and geometry variations throughout the optimization. I'll add the default stress plot available in the results section. To do this, I'll right-click on Study 2 and choose Get Initial Value. As you can see, a default stress plot from Study 2 has been added. I'll rename the plot and add Optimization to its label. Now I'll go back to the Optimization node. Enable the plot option under Output while solving, and select Stress Optimization from the list. Then, I'll click Compute to run the simulation. As you can see, the geometry updates and deforms during the optimization process, and we can observe these changes live as the solution progresses. The solution is now complete. Let's review the results. I'll enable Show Maximum and Minimum Values in the results plot. As you can see, the maximum von Mises stress is exactly 25 megapascals. To make the plot clearer, I'll switch the stress unit to MPa in the Surface 1 plot settings and click Plot again. The maximum stress now perfectly matches the upper constraint defined in the optimization setup. In the final step, let's change the color map. I'll click on Surface 1 and then hit on Change Color Table. Select Rainbow and click OK. As mentioned earlier, this is only half of the model. So, how can we view the complete geometry? We need to use a 2D mirror dataset. Right-click on the dataset, go to More 2D Datasets. Select Mirror 2D and click Plot. In the dataset settings, we can choose either Study 1 or Study 2. Let's keep it set to Study 1. I'll rename this dataset to Mirror 2D Study 1. Now, go back to the stress plot and change the dataset from Study 1 Initial to Mirror 2D Study 1. Then click Plot. As you can see, the complete geometry is now displayed. To clean up the view, uncheck the Plot Dataset Edges checkbox and click Plot again. Now let's repeat the same process for the optimized solution. We need to add another Mirror 2D dataset and set it to Study 2 Parametric Solution. Right-click on Dataset, go to More 2D Datasets, select Mirror 2D, and change the dataset to Study 2 Parametric Solution, then click Plot. Next, go to the Optimized Stress Plot and change the dataset from Study 2 to this new mirror dataset. Finally, click Plot. Again, disable Plot Dataset Edges and replot. Now we can view the full optimized geometry. And there you have it. This concludes the tutorial. Thank you for watching.